Earlier this week, I had to write some SQL update statements to fix some dirty data within one of our database tables. And the data was dirty because the name column contained duplicate values when it's supposed to, from a business logic standpoint, contain unique values. Now, even though I wrote some update statements to fix the data, I now have to go back and fix the code to prevent more dirty data from being created. And I'm going to use a transaction with a serializable isolation level. So to explore this, imagine that we have this widget table, and the widget table has name values, and those name values are supposed to be unique, but they only need to be unique at the user ID level. So theoretically, we could create a unique key on the user ID and the name columns, but for the sake of this exploration, we're going to use transaction isolations, not unique keys, in order to enforce this business constraint. We can talk about why that is later on. So to set up this exploration, imagine that I have some CRUD style DB functions here, database functions, around that widget table. So I can create a widget for a user ID and name. I can get all of the widgets for a particular user ID. And then I can check to see if a widget with a given name already exists for a particular user. So within that user, check to see if a widget with that name exists. Now, given these functions, what I'm going to do is create a test in which two asynchronous threads try to create the same widget at the same time. So if we jump over into my test template, we can see that we're including those DB functions we just looked at. We're going to generate a random user ID. We're going to generate a unique widget name. And essentially, we're going to try to create a widget record with both of these values at exactly the same time using two CF thread tags. So you can see I have CF thread competing thread 1 and CF thread competing thread 2. And if we look at the tag bodies and we just do a little command D to select duplicates, you can see that both of those tag bodies are running the exact same code. And what is that code? It is a transaction. Inside of the transaction, we're going to see if a widget with the given name already exists. If it does, we're going to throw an error. And if it doesn't exist, we're going to proceed to the create widget statement. So the goal of the two competing CF threads is that I want them to enter the transaction at basically the same time, then both run this line of code at basically the same time. And since this widget doesn't exist, both threads will see that they can proceed, and then we'll both attempt to create the same widget at exactly the same time. And then at the bottom here, we're going to wait for our asynchronous threads to join back up, and we're simply going to dump out the CF threads as well as the widgets created for that particular user. So if we jump over into our Cold Fusion code here and refresh, what we can see is that we ended up only creating a single widget for this particular user. And here are two threads out of the CF thread scope. The first one completed normally, and the second one actually ran into our custom error. So the timing didn't quite work out. Let's just refresh again. Okay, so this time, again, we only get a single user widget combination created. The first thread is the one that actually has the issue here. And if we scroll down, we can see that we have an error where the first thread runs into this deadlock while trying to execute the transaction. If we scroll down farther, we can see that thread 2 completed normally. And if we refresh again, usually we can see that different threads work out at different times. So in this case, thread 1 worked. We still only created a single user widget name combination, and this time it's the second thread that runs into the deadlock. So what's going on here? If we jump back into the Cold Fusion code and we think about what the isolation level is doing, serializable in this case means that any selects that get executed inside of the transaction get implicitly converted to row level or range level locks for our reads. So in this case, when we do isWidget with name exists, and again, if we jump into the DB function for isWidget with name exists, what we can see is that we're doing a selection using the user ID and the name. Now, what this means is that we're going to lock essentially all records where the user ID has the given value. And that means that competing transactions cannot mutate this range of records while the original transaction is still executing. So both of the transactions start at roughly the same time. They both hit this function at roughly the same time, which means that one of them, but not both of them, obtains a lock on all of the records where the user ID is the given value. Then the first transaction goes to insert a new record with the given user ID, so it's going to be in that same range, basically, of values, and it's going to be able to complete. But the second competing transaction was not able to obtain the same lock on the same users, so when it goes to create the record, it will essentially try to insert into rows that have been locked by the first transaction, and then it won't work. Now, if we were to, let's say that we remove this isolation level, and now let's go back and run this again. What you can see is that we fail to enforce the unique naming constraint. We have the same user ID and the same widget name created at two different primary keys within that table. And that's because the difference between the default isolation level, which is repeatable read, it's that this is widget with name exists doesn't end up locking the rows that it's selected during the transaction. So we really need that isolation serializable in order to lock the underlying rows so that when the transaction goes to create a record, we can block out other competing transactions from affecting the same range of user records from that